In this example, we're given a few proposed solutions to verify. So let's do that. First, we're asked to verify that the constant function n of t equals 0 is a solution. So I'm going to put 0 in for n on both sides. And I'm going to ask myself, am I getting a true equation? On the left-hand side, the derivative of 0 is 0 because the derivative of any constant is 0. And on the right-hand side, 0 times all those other numbers is going to be a 0. So yes, this constant function is a solution to the differential equation. Next, let's verify that the constant function n of t equals 1 is a solution. So this time I'm going to put the constant 1 in on both sides and ask myself if I get a true equation. On the left-hand side, the derivative is 0 because the derivative of any constant is 0. And on the right-hand side, notice that one of the factors is 0, so a product will be 0. We have a true equation, and hence n of t equals 1 is a solution. By the way, the reason I stuck the t back in here is to emphasize that n does depend on t. So like for this particular solution, if we graphed it, now this isn't a phase plot, it's just a totally normal graph. If I plot the constant function n of t equals 1, it's going to be a horizontal line. Let's verify that the constant function n of t equals 3 is a solution. So d dt of 3, is that equal to 3 times 3 minus 1 times 3 minus 3 times 3 minus 5? Yep, derivative of a constant is 0. One of the factors on the right-hand side is 0, so the product is a 0. So yeah, we have a solution. One more here. Let's verify that the constant function n of t equals 5 is a solution. Why don't you do this one? I'm sure you're perfectly capable of doing this, especially since I just did 3 very similar ones for you. So go ahead and pause the video, please, and work through part D here. How did that go? Did you remember to put the little question mark on the equals sign? If so, good job. I hope that went well for you. Now, I don't want to give you the idea that any old constant function would be a solution to the differential equation. So let's verify that the constant function n of t equals 2 is not a solution. So I'm asking myself, if I put a 2 in for n, will I have a true equation? On the left-hand side, derivative of the constant 2 is a 0. On the right-hand side, let's see, I'm going to have 2 times 1 times negative 1 times negative 3, which is, what is that? 3 times, that must be 6. Those are clearly not equal. We did not get a true equation, so n of t equals 2 is not a solution. So there's only certain constant functions that are going to be solutions. Here's a definition for you. For an autonomous differential equation, dy dt equals g of y, and I'm using this g of y notation because it's what the book uses, and I want you to be able to understand what the book is saying. G of y just means that the right-hand side, so I'm going to say stuff, with y's and constants, but no t's. So this is just a way of describing an autonomous differential equation to say on the right-hand side you've got some stuff with the dependent variable and constants, regular numbers, but not the independent variable. Anyway, a constant function y hat, so that's a little caret on top of the y, but it's pronounced hat, so y hat, that is a solution to the differential equation is said to be an equilibrium solution. And these correspond to where the phase plot intersects the horizontal axis. Here's the phase plot again for this differential equation we've been working with, and I'm going to go ahead and put the little arrows back in. If you want to pause the video and see if you can remember how to put the arrows in, that would be a good thing to do at this point. Okay, there's our arrows. Notice that where the phase plot crosses the horizontal axis, we have an equilibrium solution. So we already verified that 1, 3, and 5 are equilibrium solutions. And I'm calling those y hat because that's standard notation. Oh, and also, almost forgot this one, y hat equals 0 was a solution, and since it's a constant, that means it's an equilibrium solution. So why are constant functions called equilibrium solutions? That's how we use the word equilibrium. So from the Merriam-Webster dictionary, equilibrium is a state of balance between opposing forces or actions. So it's a state where you're in balance. You're not changing, in other words. Another word for that is steady state. And a constant is totally a steady state. Why would crossing the horizontal axis give you a equilibrium solution? Well, remember the vertical axis represents n prime and the horizontal axis represents n. So at a place where you're crossing the horizontal axis, that means n prime is 0. So n is not moving. And if a function isn't moving, it's not changing, it is constant. So similarly at 3, we have a 0 derivative. At 5, we had a 0 derivative. And at 0, we had a 0 derivative. One more definition. An equilibrium solution y hat is stable if nearby values move toward y hat. Otherwise, y hat is said to be unstable. So what's that saying? Well, let's look at this equilibrium point at 3. Suppose my population was just a little bit bigger than 3. Notice it's going to move towards the 3. Now, what if it goes too far and drifts over to the left of 3. So now my population is a little bit less than 3. Well, it's going to get pushed back toward the 3. So that is what we call a stable equilibrium. If your population goes off of that a little bit, it's going to get pushed back towards that equilibrium. So this one is called a stable equilibrium. And we have another stable one at 0. Because if you start out just a little bit bigger than 0, your population is going to decrease to 0. And of course, once you hit a 0 population, that's it. Because if you don't have any individuals to reproduce, you're just stuck there. So this one. On the other hand, if you look at the equilibrium at 1, what's going to happen if you have a population that's a little bigger than 1? Well, it's going to increase, so it's going to get pulled away from 1. So say you had a population of 1 and then a little bit got dropped in. It's not going to return to 1 because it's going to get pulled away from it. Whereas like with this stable one at 3, if you have a population of 3 and then you drop a little bit more in, it's not going to go away from 3, it's going to go back towards the 3. So it stabilizes at 3. Whereas this one at 1, if it goes off the 1, it's not going to stabilize at 1, it's going to keep moving away. So this one is unstable. And similarly, the one at 5 you can see is unstable because the arrows are pointing away from it.